physics. So this is my lecture 1.
So Sayantan, just one thing. So is it okay if we record it?
Yes, this is fine.
Okay. Thank you.
Okay, so I will be discussing about the basics of the standard model of particle physics. So as you know, the standard model is one of the most successful description of our world around us about the elementary particles and the interactions. So the standard model is a framework to understand the different particles, fundamental particles, and their interactions. Of course, I should tell you at the beginning that the standard model is not the complete theory, and I will discuss about this later. It's just a model in that sense, but it is some kind of a low energy effective theory that has been tested in different experiments, Alice being one of them, and it is seen that this model is valid up to very high precision with all whatever experimental results are available. So this is one of the most successful models, but again, I should emphasize that this is not an exact theory of the interactions of elementary particles, but it is a low energy effective theory. So standard model, as you can see, this is a picture that was taken from Wikipedia, and it is shared from the Fermilab, where they show whatever are the different constituents of the standard model. So if you look at this table, then you will see that there are these, they have divided into 2 categories. So first category is in the left hand side. So these first 3 blocks. So these are called 3 generations of matter, and they are mainly fermionic. So they consist of quarks. There are 6 quarks, families of quarks, which is this, there are 3 families of quarks, but 6 flavors: up, down, charm, and strange, and the top and the bottom quarks. And then there are these leptons. So the electrons, muons, and the taus, and the neutrinos of different flavors, which is the electron neutrino, muon neutrino, and the tau neutrino. So these are all fermionic species, and their masses are very well known by now. And as you know, the discovery of these particles led to several Nobel Prizes in particle physics. And the latest was the discovery of the top quarks, which was discovered in Fermilab. Now, these are the particles that make the universe that is around us. But of course, there are interactions between the particles. And those interactions are characterized by the different force carriers, which is in this left-hand side, in the right-hand side of this figure. There are these gauge bosons, which carry the forces. So one of them is the gluon, which are the carriers of the strong force. The photons are the carriers of the weak, or the electromagnetic forces. And then there are the W and the Z bosons, which are the gauge bosons, which carry the information of the weak forces. Now, these are the carriers which carry the information of the forces. And so as you can see, there are 3 types of interactions that are known. One is the strong interactions, one electromagnetic, and the other is the weak interactions. And then there's this famous Higgs boson, which is responsible for giving mass to all these fundamental particles. So the discovery of Higgs boson was one of the milestones from the LHC experiment. And so, um, so this is responsible for giving masses to all these fundamental particles. Of course, you may ask, what about the mass of the visible matter around us? So the visible matter consists of different atoms named hydrogen, and the mass of those hydrogen is due to protons and neutrons, and those actually come from strong interactions. So even though the Higgs is responsible for giving masses to all these fundamental particles, but it doesn't amount to explaining the mass of the visible matter around us. So 99% of the mass of the visible matter around us is due to strong interactions, uh, which is caused by a theory called QCD, which will come in the later half of the talks, and also by the next lecture by Professor Sandeep Chatterjee. So to summarize, the standard model is nothing but understanding the different particles, their quantum numbers, their interactions, and how they get their masses, and what can we know about the different cross sections that happen due to interaction between these particles. So in these lectures, we will deal with all of these topics one by one. So, so the interactions that we normally see around us, the most common amongst them is electromagnetism, which was known quite early, before the advent of the 20th century, and they were characterized by the Maxwell's equation. And in the famous Rutherford scattering experiment, it was realized that uh, any atom consists not only of these electrons, which were discovered in the later half of the 19th century, then there are also positively charged nucleus within the atom. And the nucleus cannot be consisting of just positive particles, because if there are so many positive particles and nothing to stabilize them, then that forms an unstable system. So there were some neutral particles also inside, and they interact strongly to give stability to this nucleus. And of course, as you know, since you all will be budding into you will be budding experimentalists, so you know that detecting charged particles is easy, because Rutherford scattering was one of the first seminal experiments of this sort. Of course, there were also cathode ray experiments, but the main philosophy there was to bombard target with a charged particle, and then look at the scattered particles that come out of the collision, and then from the scattering angle idea about the charge of the particles inside the target. So that was the famous Rutherford scattering, from where he identified that inside a nucleon, inside an atom, there are only small charge centers which has negative charges due to the electrons, but there is a massive positively charged central region or cloud, from where the alpha particles that were used to bombard the gold foils, they scatter almost in opposite directions. They scattered very heavily. And from there, the idea about the nucleus of an atom came. But of course, it was hypothesized that there are neutral particles inside the nucleus. And it is very difficult to detect a neutral particle. But this was this very ingenious experiment by James Chadwick, which is one of the milestones in particle physics research, where he discovered neutrons. And with the discovery of neutrons, it was seen that the neutron mass comes out to be 939 MeV 0.507, which is very close to the proton mass. Sorry, there was some mistake here. The proton mass, I didn't update it. So yeah, so the main point is the neutrons and the protons are very close to each other. And does this tell us anything about the symmetries or any symmetry that causes these masses to be degenerate? So this was one of the issues that was addressed by Heisenberg, and he proposed that this experimental observation may allude to the fact that neutrons and protons are the degenerate states of the same quantum number. And this quantum number is named as isospin. So since their properties are very, since their masses are very close to each other, and they interact in a similar manner, which was also seen in the experiments, then it led to the conclusion that there may be some symmetry which tells us that there are degenerate states corresponding to that symmetry. And that is called the isospin. So one use this quantum number for the isospin denoted by I. So I represents the isospin, and then one can also write the component of the total isospin, which is given by this I3. So since protons and neutrons have the same isospin, the only way to differentiate between them is from the component of the total isospin. So if one writes the wave function of the proton in this fashion, so this corresponds to wave function of the proton. It consists of these quantum numbers. So the x and t corresponds to the space-time coordinates. The s, of course, corresponds to the spin of the proton, because as you know, these are fermionic particles, so the spin enters here. And of course, then this isospin also enters, where I is the total isospin and I3 is the component. We call it third component of the isospin. So for the proton, it is a value which is I3, and for the neutron, which it is a value of minus I3. So for the discussions henceforth, I will not show the other quantum numbers like the space-time and the spin explicitly. I would just do every calculation in the isospin space. So as I was mentioning, so since these protons and neutrons have degenerate masses, so one can think of them as a doublet consisting of these two states, which is given by characterized by the different sign of the third component of the isospin. So now how do we see that these are the doublets of the proton? So when you look at the structure of these two component states, you can make a correspondence with the spin half particles. So as you know, in the spin half particles also, the spin half particle has two projections, one up and down. And you can think of protons and neutrons in the similar fashion, but in the isospin space. So it has same isospin quantum number, but the projectors are up and down. So once you have this, then one can denote the third component of the isospin as the quantum numbers of this operator sigma 3, which is the third Pauli matrix. And if you act this isospin operator I3 on these states, then you should recover plus minus half of corresponding to proton and the neutron states. So I think these things you can see an analogy with your spin problem that you learned before in quantum mechanics. So now the next question is how to see that these neutrons and protons um, the components of the same quantum number. Before I go to that, I should just again let you know that these neutrons and protons, as you can see, they are the eigenstates of this sigma 3 operator with a factor of half. And what do you know about the properties of the sigma 3? So what type of matrix is that? So anyone, any of your students can answer this?
It is traceless and Hermitian.
Yeah, so it is a Hermitian operator. So as you know that any physical state should be eigenstates of the Hermitian operator. So this is traceless and Hermitian. So now since you have told that these are traceless and Hermitian, you can show that any unitary matrix can be written in terms of an exponential of these traceless Hermitian operators. So I guess you are familiar with this, that this sigma 3 and all of these Hermitian operators, you can show that these are generators of your SU2 group, so unitary group, which is SU2. One of the most fundamental facts that also comes in different areas of particle physics. So usually what happens is if you know the symmetry of the symmetric group of your particles or of your system, then you can write the symmetry group as you can write the symmetry group in terms of its generators. So like here, as you can see that the sigma 3 are the generators of SU2, which you must have learned before. So similarly, it is a most general technique where you can find out the symmetry group first and then construct the generators of the symmetry group. And once you know the generators of the symmetry group, then the physical states of the system are the eigenstates of your generator. So that is what I showed here. So here, of course, I was discussing of a specific symmetry group, which is the isospin. And here the isospin, the eigenstates of this isospin symmetry group are the neutrons and the protons. And as you can show that these neutrons and protons are eigenstates of your sigma 3, which is the generator of your SU2. Once you know the and okay, so before I go into the more into the discussion from your spin algebra that you learned in quantum mechanics, suppose you have any spin state with the quantum number I, it has 2I plus 1 degeneracies. So this is another way to look into the fact that neutrons and protons have isospin half, because you can show that since there's a twofold degeneracy because neutrons and protons are components of the same state and they almost degenerate. So then you can use that fact to argue that indeed your isospin of the system is half. Because your degeneracy is given by this formula 2i plus 1, and this 2i plus 1 is equal to 2 because you have two states, which will give you the isospin to be half. So then, of course, if you have the isospin, then you can use, if you know how to represent your third component of the isospin in terms of the operator, then of course you can construct the raising and the lowering operators. So the raising and the lowering operators are described in terms of the two sigma matrices, sigma 1 and sigma 2, and defined in this form. So I plus minus is sigma 1 plus minus I sigma 2 normalized by 2. You can show that the I plus is given in this form. It is a 2 cross 2 matrix with only a 1 in the off diagonal component, the top right corner of the matrix. So this is given by here. And all the other entries are 0. So, and of course, you can construct the I minus. Now, you can use this fact and so what will happen, suppose if I use I plus on a proton state. So you know the proton state is of this form. Then can someone answer what will happen if I use I plus on that? Anyone? Okay, so let me show you.
Yeah.
No, the I plus acting on a proton state. So the proton is here,
One.
given by this.
Yeah, so
So what will happen when I plus acts on a proton?
0.
Yes. So the proton is the highest weight state. So you cannot go beyond that. It's a doublet with the highest component of the isospin being proton. So if you act this on the proton, then it's 0. And you can also show that if you act I plus on the neutron state, then you get back a proton. So it is like a ladder operator. It takes you from a state with the lower component of isospin to a state with a higher component of the isospin. So, and similarly, you can prove these relations. I minus, when you act I minus on the proton, I minus is the lowering operator. It takes you from the higher isospin state to the lower isospin state. And similarly, I minus acting on the neutron will be 0. So I am doing this slowly because we will use these facts very extensively. So you should be comfortable with these notations because later on I will just use these facts to construct different states and more symmetries of the problem. So are there any further questions here? I can take them, otherwise I will go ahead.
Yes, sir. So when
Yeah.
I minus acts on the proton state and gives neutron state, what happens to
Yeah.
the charge conservation?
So here we are not looking at the electromagnetic forces. We are only talking about strong interactions. Or these are degenerate. Of course, due to electromagnetism, the degeneracy is broken a bit in that sense because if you look at the particle data book, you will see that the masses of the proton and neutrons are not exactly equal, but they are a little bit small discrepancy. They come due to different factors, and one of them is electromagnetism. So yes, the electromagnetism indeed breaks the degeneracy, but when you just consider strong interactions without looking into electromagnetic and other interactions for the time being, then under strong interactions, protons and neutrons are exactly degenerate components of the same isospin state. Okay, are there any further questions? Okay, so then let's move on. So after the World War, it was a very exciting time because during the World War, most of the scientists were involved in different projects related to the war. But after that, they were free to do their scientific research. And there were beautiful experiments done. One of these were done by Cecil Powell and his group uh, in Bristol. And what they used to do is to look at cosmic ray particles. So, do anyone know about cosmic rays? So what are these? Have you heard about cosmic rays? Can anyone tell me what are these cosmic ray particles?
So these are particles, basically high energy particles, which are coming from the outer space and continuously crossing us. And these basically
Yeah.
contains high energy particles. Basically, these are
Mhm.
created during the time of Big Bang.
Even from other processes also, yeah, not only big bang. So yeah, so these are very high energy particles. Do you know what is the energy range of these particles?
Can't remember exactly right now.
So yeah, so check out what are the energy ranges of these. So they are very high energy TeV or even more, and so those cosmic rays, these are mainly highly accelerated charged particles, mainly protons, and they enter the atmosphere and interact with the atmosphere to produce different other particles. And then um, there was this photo emulsion techniques that were used by Cecil Powell and his group. So they used to put in this photo emulsion films on very high mountains, on top of very high mountains. And from there, these particles used to leave tracks on these films. And then from there, they used to detect those particles. So in 1945, they discovered these particles, pions. So the existence of these particles were um, speculated, or sorry, not I should not say speculated, but it was theorized by Yukawa. So he believed that these are they named as mesons, or mesons meaning temporary particles, which carry the information of the strong force. And these pions are some of these particles. So they also interact strongly. So how do we know that they interact strongly versus electromagnetism? Because you can see that the typical rates of electromagnetic scattering and the time scales involved are much larger than the time scale involved in the reactions of these particles. So that's why they call that these particles interact strongly. And then they discovered first the neutral pions and also the charged pions. And they also saw that their masses are quite close. So the neutral pions have masses 135 eV, have masses about 140 maybe, close to that. So again, there's a tantalizing hint that they may be degenerate states under strong interactions. And so then there are these three states which are degenerate under strong interactions. So now, if there are three states which are degenerate, then can you guess the isospin of the system? Sorry? Didn't hear you. Yes, very good. It's 1. So you can show that the degeneracy is given 2i plus 1, which is 3. So it will give you I equal to 1. So these are also SU2 states, but now the isospin quantum number is 1. So there are 3 states. So you can label them according to the is the highest state, which has a quantum number of, the isospin is 1 and the projector is also 1. Pi minus is 1 minus 1 and pi 0 is the state with 1. And the I3 or the third component of isospin is 0. So these are these three states that you get. So, and of course, it was also observed that strong interactions conserve isospin. So that was observed using, by looking at the interactions of 2 protons and 2 neutrons scattering experiments. So they're of the same strength. And mathematically, you can write in terms of, in quantum mechanical language, that if you know the Hamiltonian that has the information of the strong forces or the strong interactions, then the Hamiltonian H strong commutes with the isospin operator. So, okay, so then the fact that isospin is conserved in strong interactions can be used to understand different physical processes. For example, if you want to look at the scattering rates of strong interactions. So if you have the scattering between pi minus and a proton, then it may go to pi minus and a proton, or pi 0 and a neutron. And one has to calculate the relative cross sections of these two processes. So, to do that, one has to use the concept of product states. So how do you use that? So, first of all, here the total isospin is conserved, so you can add the total isospin. So here the total I should be equal to the I of the proton, the total isospin of the proton, and the isospin of the pion system. So here the proton belongs to isospin half system and the pions belong to isospin 1 system. And then what will happen if you add 2 isospins? It is similar to addition of 2 spins. You have a spin half and a spin 1. So what will you get as the total spin? And what are the projectors? Can anyone answer that? Hello? Hello?
Total isospin will be 3 half and half, and the third component will be for 3 half. There will be 3 half and half.
Yeah. So if you add 2 isospins, 1 and half, then there can be, so the addition will give you either, so the highest weight state is given by this. So the addition will lead to this highest weight state, which is 3 half, and this 3 half state has how many components?
2 components, 3 half, and 3 half, half.
No.
4 components.
So, yeah. So it should have 4 components. So it has 3 half, half, minus half, and minus 3 halves. So you can write the highest weight state where you take the proton and the pi plus. So the pi plus is given by this 1, 1, and the proton is given by half, half. And this highest weight state is uniquely determined in, and that only gives this 3 half, 3 half state. Because this is the highest weight, because the isospin components of these two constituent states of the pion and the proton are the maximum. So it will give you the maximum combined state, which is 3/2 3/2. So the highest state in this whole problem. So now, once you know the highest state, then of course you can act so the lowering operator is the sum of the lowering operator of the proton and the pion states. And remember that you know that
Hello, can you hear me? Hello.
Yes, yes, we can hear you.
Oh, looks like there is some internet issue with Sayantan. So,
hello, can you hear me?
yes, Sayantan, we
Yes,
can
sir.
hear you now.
Okay. Okay. So sorry, I was a bit disconnected. So yeah. So as I was mentioning that the highest weight state, then one can use the lowering operators acting on the highest weight state to get all the other constituent states. For example, and one should also realize that acting I minus on the total state is same as the sum of the lowering operator on the proton and the pions. So then I minus acting on this highest weight state, 3/2 3/2, will give you 3/2 and half. And I have taken out the factors and appropriately normalized in the right hand. Then since I know how to write this highest weight state, 3/2 3/2 in terms of all these constituent states, half, sorry. Okay, so so I just had a question that this green state, can you identify this green state that is there written in terms of this constituent states? Anyone? So this green state
Plus neutron.
Yeah, this is a pi plus a neutron. So now we want to calculate what will happen to this cross section. So I need pi 0 and a neutron. So then you have to act the isospin lowering operator again on these states because the blue state is 1 0 and half. So this 1 0 is nothing but your pi 0 and the proton. You need a neutron state. So you have to act the I minus again on this. And then you can show that both the states pi minus p and pi 0 n, they contribute to this state, which is 3 halves and minus half, with weights 1 by square root of 3 and 2 by square root of 3 respectively. So you act I minus on these states again, and then you can show that that has contributions from both pi 0 n and pi minus p with these weights. So the point is that when these interactions happen, so pi minus p has the quantum numbers which corresponds to this intermediate state, which is 3 halves and minus half. So it goes through this intermediate states and decays into this pi 0 n. So you have to find out these intermediate states and then write it in terms of these components. And then one can calculate the cross sections. So since the cross section are probability densities, so you have to do a mod square of the probability densities. And then you can show that since pi minus p comes with an amplitude 1 by square root of 3 and the other one as square root of 2/3, then you take a mod square of it, and then you will see that the ratio of cross sections is 1:2. And in fact, if you look at the particle data book, you will see that they are very close to each other. So this is one of the applications of isospin. And so I will end with something on the strangeness. So immediately after discovery of pions, there were kaons which were discovered in cosmic ray experiments. And then advent of cyclotrons also enabled discovery of many of these heavy spin half integer particles. And it was observed that some of these particles are long-lived on the scale of strong interactions. Like, for example, the sigma minus. This is produced by strong interactions of pi minus and proton. And it goes to K plus and sigma minus. But decays very weakly to neutron and pions. Whereas there were some other baryons which were found out. So these spin half heavy particles were called baryons. So not spin half, but yeah, half integer spins. This delta goes to neutron and pion. So this delta going to neutron and pion happens at a very quicker time scale compared to the decay of sigma minus to neutron and pion. So that tells us that this delta and the sigma minus have something which is not in common. And also, it also tells you that if you look at the production mechanism of the sigma minus, then it comes with a K plus. So all of these particles, which were produced in strong interactions and decay very weakly, they come coupled to the specific particles, K plus or so that led to the speculation by Gell-Mann and Nishijima to introduce a new quantum number called strangeness. Of course, this has been experimentally now verified, so it is no longer speculation now, and the strangeness is another quantum number. So now one can characterize these particles like delta has a strangeness 0, whereas these kaons and sigma has a strangeness 1 with different components. So I will now in the next class do more on how to include both strangeness and isospin and characterize the different hadronic states. So if you have any questions, you can ask now.
Hello, sir.
Yeah.
So I had these questions on the very first slide
Mhm.
where you explained, you basically said about the standard model.
Yeah.
So in explaining the standard model, you mentioned at some point, you said that this is a low energy effective theory.
Yeah.
Could you please tell something more about this? What is exactly this low energy effective theory is, and something maybe more to it?
Yeah, so in strong interactions, in standard model, as you know, there are many unresolved issues if you heard about it.
Yeah.
First of all, is standard model is not renormalizable. There's a scale in the problem, and the scale is the scale at which the electroweak symmetry is broken.
Mm-hmm.
So in that sense, the standard model is defined only up to that scale. So that is why it is an effective theory. If you have heard about Fermi's theory of beta decay, you will
Yeah.
also realize that the Fermi's theory of beta decay is also an effective theory, which is defined up to the scale defined by this W and Z boson masses. So it is not an exact theory. The exact theory of weak interactions is the electroweak theory that we will do. So the Fermi theory of weak interactions is just an effective theory of this electroweak sector. So similarly, standard model is an effective theory, and of course the full theory is not yet known. Whether you include supersymmetry or how to do the ultraviolet completion of the theory is not known till now.
Okay. Okay. So this basically this scale or the limit that actually put the restriction.
Yeah.
Okay.
So in our world, standard model is a very good effective theory. We
Yeah.
know that all of these masses are known to very high precision. All the cross sections are known to very high precision, whatever is known in standard model. But there are many things which tell you that standard model is not a complete theory. Like you cannot explain the baryon asymmetry in the universe, the neutrino masses, etc. within the standard model. So that's why standard model is not the complete theory.
Complete theory. Yeah.
I will come to that in the last lecture, a bit of it.
Okay. Fine. Thank you, sir.
Are there any further questions? So I introduced these concepts very slowly, but next class I will use these to construct the quark model that was discovered by Gelman. And I will use these results quite frequently. So that's why I wanted in a relaxed manner.
So
Okay.
can you go to the 8th slide?
Yeah. Last one.
The last bit one.
Yeah. Oh. This one.
Yeah, before that. Yeah, so what's the reason for different weights, for these two channels or something? Like when pi minus p goes to pi minus p or pi 0 n,
Yeah.
and there are two different weights.
Yeah.
So like at this point, we are not considering the different masses for proton and neutron, or
Yes,
pi 0
that
or
is
pi
true.
plus pi. So what's the reason for different weights or different probabilities for these two reactions?
Oh, this comes just directly from the angular momentum algebra. So as I was showing here, that you can just use the lowering operators and show that this state 3/2 and -12 has contribution both from the pi minus p as well as pi 0 and n with these two weights. And this comes directly from this using this lowering operator on these states. So I just showed the first step. So you have the highest weight state, you act I minus on it, then you will get these two states. But as we discussed, this one doesn't have pi minus p, neither it has pi 0 n, because it is pi 0 p. So you have to again act I minus on this. So this is an assignment for you all. So act the I minus, and then you can show that the next state of this multiplet, 3/2 and -12, has contribution both from pi minus p and pi 0 n with these weights. So this tells you that this reaction that was written here goes through this 3/2 state. 3½ minus half state. So this is the combined state that it goes through, and then from there you can calculate the weights easily. So
Okay, I was like asking for the physical significance, like conservation of mass or something, energy.
so the significance is that if you look at, so here what we are assuming is that strong interactions conserve isospin. So using that fact, we are using this angular momentum states to calculate the cross sections. Angular momentum in isospin states, because they have the same algebra as the angular momentum. So
Okay, thank you.
yeah, if you look at the particle data book, you should look at these cross sections of these two reactions. And then you should convince yourself that indeed they come as this ratio. There is a little bit difference, but that comes due to other factors like electromagnetism, which is not taken into account here. Here, we are assuming that there is only strong interactions. And since isospin is conserved within strong interactions, I use all the isospin algebra to predict these kind of cross sections.
Thank you, sir.
Okay, you're welcome. So you can verify, everyone can look at the particle data booklet, see the cross sections of these two reactions, and then see whether how close it is to the calculation that we did here. Okay, so if there are no further questions, I will end here and we will start the next tomorrow. Thank you.
Sayantan?
Yeah.
Yeah, so this is Partha Bhaduri from VCC. So I have one query actually. So would you
Yeah.
Partho, we cannot hear you. I do not know.
I cannot hear you.
hello? Okay.
Yeah.
So would you, while discussing tomorrow, would you also discuss about like coupling constant, this and running coupling constant, and with features like asymptotic freedom, infrared slavery? Will you discuss all those things?
That is at the last lecture. Yeah.
Okay. Okay.
But not the details here.
Okay. Okay. And the two transitions in QCD, like your chiral transitions and deconfinement transitions, do you have plans to discuss those?
No, I guess that will be discussed in the lectures by Sandeep.
Okay. 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 Thank you.
Yeah, thanks.
Okay, so I think we thanks Sayantan again, and we are already